Hello everyone, this is Dr. K. Evangeline Supriya, Associate Professor of Physics, Department of Humanities and Science, SRIT Engineering College, Anantapur, Andhra Pradesh. Today I am going to present the Engineering Physics syllabus, unit number 2, that is crystal systems. So in the crystal system, first of all we should study the matter. Matter in universe is mainly classified into three kinds. One is solids, another one is liquids, and another one is gases. Solids means all atoms or molecules are arranged in a fixed manner and have definite shape and size. Liquids and gases are the atoms or molecules are not fixed and cannot form any shape or size. They gain the shape and size of the container. So we should study about now solids. There are two types of solids. One is crystalline solids and amorphous solids. So crystalline solids are long range orderly arrangement of constituents, and amorphous solids are short range random arrangement of constituents. They are definitely definite in shape, they are irregular in shape. They are the crystalline solids are anisotropic in nature, and amorphous solids are mostly like liquids. They are crystalline solids are true solids, and amorphous solids are considered as pseudo solids or supercooled liquids. It has crystalline solids have definite heat of fusion, and amorphous solids have heat of fusion is not definite. Crystalline solids have strong and sharp melting points, and amorphous solids often soften a range of temperature and so can be moduled. So the examples for the crystalline solids are sodium chloride, diamond, etc. And the examples for the amorphous solids are rubber, plastics, and glasses, etc. You can see in the figure here in the crystalline solids are in an orderly arrangement, but in the amorphous solids they are randomly arranged. These are the main differences between crystalline solids and amorphous solids. So before going to enter into the unit, we should know some basic definitions regarding the crystal system. First one is lattice. So the regularly orderly arrangement of atoms or molecules in three-dimensional pattern is nothing but lattice. Basis means certain atoms or molecules are attached to each lattice point in a crystal structure. These atoms or molecules attached to any lattice point identical in composition, arrangement and orientation form the basis of a crystal lattice. So the formula for the crystal lattice is equals to basis plus crystal lattice. And what do you mean by unit cell? The smallest repeating unit of a crystal lattice is nothing but the smallest building block which repeats regularly is nothing but a unit cell. It is when translated in three dimensions, it can generate the entire crystal structure. The fundamental grouping of particles which are repeating entities is nothing but unit cell. As you can see, it is having the one-dimensional unit cell, two-dimensional unit cell and three-dimensional unit cell. So the repeating the unit cell over and over again in all direction builds the macroscopic crystal structure. So how it represents properties means it contains all the necessary information to describe the symmetry and the properties of the crystal, including its dimensions and the arrangement of its atoms, molecules or ions. In the dimensions, a unit cell is defined by 6 lattice parameters, that is the length of 3 axes and 3 angles and 3 lattice points. The positions of the atoms or ions within the unit cell are represented by fractional coordinates. So what are called lattice parameters? The lattice constant or lattice parameters refers to the physical dimension of unit cell in a crystal lattice. Lattices in three dimensions generally have three lattice constants refers to as A, B, C along the X, Y, Z axis. So on the basis of the lattice parameters or shape of the unit cell, crystal systems are classified into 7 categories. You can see here cubic, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral or hexagonal. In the cubic cell, all the lattice parameters, that is ABC, all the axes and all the lattice angles, yeah, alpha, beta, gamma are equivalent to 90 degrees. In the tetragonal, first two axes are equal and which is not equals to third axis. That is why it is having A is equals to B, which is not equals to C. And the coming to the angles, lattice angles, all the three angles are perpendicular to each other. That's why it is having alpha is equals to beta is equals to gamma is equals to 90 degrees. In the orthorhombic, all the sides are not equals to each other. That's why it is having A is not equals to B, B is not equals to C. And all the angles are right angle perpendicular to each other. Comes to the monoclinic, all the sides are not equal, where alpha and gamma are equals to 90, where one angle is not equivalent to 90 degrees. Coming to the triclinic, all the angles and all the sides are not at all equal. Coming to the trigonal, all the sides are equal, all the angles are not perpendicular to each other. Hexagonal, all the two sides are equal and third side is not equivalent. Two sides are perpendicular to each other, that is 90 degrees, and gamma is equals to 120. So these are the 7 figures regarding to 7 crystal systems you can see here: cubic, orthogonal, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral and hexagonal. So these are the Bravais lattices: simple or primitive, base centered, face centered, and then so the crystal systems and primitive lattices. For the crystal systems, cubic, it is having the PIF. You can see here P is representing primitive cell, I is representing body centered cell, and F is representing face centered cell. Again in the tetragonal it is having PI, primitive body centered. For the orthorhombic it is having 4 types of unit cell: PIFC. P is primitive, body centered, face centered and side centered. For the hexagonal it is having only P, that is primitive, and the monoclinic it is having the primitive and side centered. For the triclinic it is having the primitive. So these are the crystal systems and its respective Bravais lattices. So these are the we have tabulated all the details regarding the 7 crystal systems. You can see here for the cubic it is having the axial ratios, angles, number of Bravais lattices are 3, types of Bravais lattices are P, BCC, FCC, and examples for the cubic is sodium chloride and potassium chloride, Ag, Au. For the orthorhombic it is having axial ratios, axial angles, which I have explained earlier, and number of Bravais lattices are 4, primitive, BCC, FCC and EC, 3-folded axis. And then for the example are barium, BaSO4, MgSO4 and KNO3. For the tetragonal it is having axial ratios, axial angles, number of Bravais lattices are 2, types of Bravais lattices are primitive, BCC, and then example is SNTiO2 and NiSO4. For the monoclinic it is having the 2 types of Bravais lattices and gypsum, FeSO4. And then for the triclinic it is having the only 1 Bravais lattices, that is primitive. For the triclinic, hexagonal and the rhombohedral, only they are having the only 1 Bravais lattices, that is only primitive. So the examples to the respective crystal system is tabulated in the example column. As you can see here, these are the in detail analysis of properties of 7 crystal systems. Now some important definitions regarding the crystal systems are: atomic radius, the half of the distance between any 2 successive atoms in a crystal lattice is nothing but atomic radius, and void space means the empty space available in the crystal system. Crystal lattice with atoms occupying their respective positions is called void space, and nearest neighbor distance, the distance between 2 nearest neighboring atoms in a crystal lattice is nothing but nearest neighboring distance. Effective number of atoms per unit cell, the total number of atoms in a unit cell by considering the contribution of corner atoms, center atoms and face centered atoms is nothing but effective number of atoms per unit cell. Coordination number means the number of equidistant neighbors that an atom has in a crystal lattice is nothing but the coordination number. So atomic packing factor formula is the total volume occupied by atoms in a unit cell to the volume of the unit cell. That is the ratio between total volume occupied by the atoms in a unit cell to the volume of the unit cell is nothing but atomic packing factor. So we should study the now simple cubic crystal structure. A simple cubic crystal structure is the most basic cubic lattice featuring an atom or lattice point located at each of the 8 corners of a cube shaped unit cell. Because each corner atom is shaped by the 8 unit cell, there are effectively only 1 atom per unit cell in the simple cubic structure. Below is the simple cubic structure, you can see, and the properties of the simple cubic structure we can see. It has a corner atom is shaped by 8 unit cell. So the contribution for the corner atom is 1 by 8. Cube has 8 corners, hence the contribution is 1 by 8 into 8 is equals to 1. So the number of atoms per unit cell is 1 and the coordination number n is equals to 6 and the radius is equals to r is equals to a. Atomic radius r is equals to a by t. A by 2, the volume occupied by one atom in the simple cubic is 4 by 3 pi r cube. Lattice constant a is equals to 2r. Volume of the unit cell v is equals to a cube. Atomic packing factor, the formula which I have explained here, the total volume occupied by atoms in a unit cell to the volume of the unit cell. Through that formula we will get the 52% of the volume of the simple cubic unit cell is occupied by atoms. So the APF factor, which is a very important factor for any crystal structure, that is 48% APF for the simple cubic structure. The examples are, so many examples are there. I have included some potassium crystal. So the next crystal is BCC, that is body centered cubic structure. A body centered cubic structure is a crystal lattice where atoms are positioned at each corner of a cube and one atom is located in the exact center of the cube, making a total of 2 atoms per unit cell. As you can see here, this is the crystal structure regarding the base centered cubic. So in the base centered cubic, where atoms are positioned at 8 corners of the cube and at the very center of the cube. So the lattice parameters, you can see all the sides are equal, all the lattice angles are perpendicular to each other, that is 90 degrees, and a primitive cell consists of a center atom along corner atom. So it is not a primitive cell. So the total number of atoms contributed by corner atoms is 2. The number of atoms present in a unit cell is 2. Coordination number, the nearest neighbor of a body is a centered atom and is a corner atom. So it is surrounded by 8 corner atoms. That's why the coordination number is 8. So the volume of the volume of one atom in BCC structure V is equals to 4 by 3 pi r cube. The volume of one unit cell V is equals to a cube. Atomic radius r is equals to root 3 by 4a. Atomic packing factor is equals to 0.68. So in the previous section, that is for SCC, for simple cubic, you can see here it is having the atomic packing factor for 48%, and coming to the BCC, the atomic packing factor it is having 68%, that is 0.68. Now we can see the face centered cubic is a crystal lattice where atoms are located at each corner and at the center of each face of a cube, resulting in 4 atoms per unit cell and a close packed structure with 74% volume occupied by the atoms. This close packing gives FCC materials high ductility and toughness, and common examples included are aluminum, copper, silver and gold are the few examples for the face centered cubic. Below is the figure, you can see this is the face centered cubic, and in order to determine the atomic radius, this is the figure. So coming to the properties for the lattice parameters, already we have seen earlier in the earlier slides. All the angles are perpendicular to each other, that is 90 degrees. All the sides are equal to each other. So it is not a primitive cell and the unit cell is cubic unit cell. So the effective number of atoms in each and every face-centered atom is shared by two unit cell. The total number of unit cells is 4. The coordination number, there are 12 points surrounding nearest neighbor of a body-centered atom is a corner atom. So the coordination number is 12. The volume of one atom in the face-centered cubic is 4 by 3 pi r cube. So the volume of one atom in the face-centered cubic B is equals to A cube. Atomic radius R is equals to root A by 2 root 2. Atomic packing factor is 74. Thus 74% of the volume of an FCC unit cell is occupied by atoms. It is a very closely packed structure than the simple cubic and BCC. So atomic packing factor, as you can see, for the simple cubic it is 52%, and for the body centered cube it is 68%, and for the face centered cube it is 74%. Thus the atomic packing factor is more for FCC. Hence FCC is the more closed packed structure when compared to the SC and BCC. This is an important point we should remember. Atomic packing factor is more for FCC. Hence FCC crystal system, that is face centered crystal systems, are morely closest packed structure when compared to SC and BCC. Now we can see the entire properties we have tabulated in this table. The properties: type of unit cell, number of atoms per unit cell, coordination number, nearest neighboring distance, volume of one unit cell, atomic radius, atomic packing factor, type of packing. You can see for the simple cubic and body centered cubic it is very loosely packed, and coming to the face centered cubic it is closely packed. So the examples, for the few examples I have enlisted here, listed in the table. One is for the simple cubic SC, it is polonium and CaCl, and for the body centered cubic it is sodium, potassium, lithium and iron. For the face centered cubic it is NaCl, Au, As and Cu. So these are the few properties we have listed. We have covered all the properties for the three crystal systems, that is simple cubic, body centered cubic and face centered cubic. Now the next topic is Miller indices. What exactly the Miller indices means? Miller indices are the set of three integers denoted as HKL that symbolically represent a specific crystallographic plane or direction within a crystal lattice. Crystallographic axis with fractions clear to obtain with the smallest possible integers. This system actually firstly developed by William Hallowes Miller in 1839. It provides a convenient and standardized way to identify and prescribe the planes and directions, especially in the crystal systems. That is why it is called as, these indices are discovered by Miller, that's why it is called as Miller indices. So there are steps to determine the Miller indices for any type of crystal structure. First one is to identify the intercepts. As you can see, this is the plane XYZ plane. To identify the points, find the points where the crystalline intersects the three crystallographic axes ABC, and we have to write the intercepts. Express the intercepts as a fraction of the unit cell edge lengths. Example 2A, 3B and 2C. If a plane is parallel to an axis, its intercept is infinity. And the third one is, you have to take the reciprocals of that intercepts. You can see here the example 1 by 2, 1 by 3 and 1 by 2. And clear fractions. To clear the fractions, we have to multiply the reciprocals by a common factor to obtain the smallest set of integers. We can see here we will get 3, 2, 3. Now after getting these values, we have to enclose these integers in a parenthesis, placing the resulting integers in parenthesis without comma to get the Miller indices. First point is Miller indices are the three set of integers which are denoted as HKL plane that symbolically represents a specific crystallographic plane or direction within a crystal lattice. It was discovered by William Miller in 1839. There are 5 points. First one is to identify the intercepts, and second one is write the intercepts, and third one is take the reciprocals, and fourth one is clear fractions, and fifth one is we have to enclose those integers in the closed parenthesis. This is about Miller indices. Now, the separation between successive HKL plane in a cubic lattice or interplanar spacing D. Consider a plane ABC intersecting all the three axes XYZ. Let OA, OB, OC. You can see here in the graph interplanar spacing figure I have given OA, OB, OC, or the intercepts made on the orthogonal axis 0x, 0y, 0z. ON is the perpendicular from the origin to the plane. D is the interplanar spacing distance. Alpha, beta, gamma are the three angles. So after deriving we have here the formation of three triangles ONA, ONB and ONC. From the law of the directional cosines, we are having the cos square alpha plus cos square beta plus cos square gamma is equals to 1. Then we will get d square by a square is equal, d square is equals to a square by h square plus k square plus l square. D is equals to a by square root of h square plus k square plus l square, which is known as interplanar spacing, which is denoted by small d. Now, X-ray diffraction by crystal planes. The diffraction, already in the first unit wave topics I have mentioned the property of diffraction. What exactly the diffraction means? Bending of light ray around the corners of an obstacle is nothing but diffraction. Now, the diffraction of the light is the bending of light waves around the obstacle in their path. It was discovered when the wavelength of the incident light is comparable with the width of the obstacle. Now, the grating is a glass plate on which there are ruled lines. I have explained grating in the previous lecture video, that is the unit 1 wave optics. Grating is nothing but a optical device which consists of equal number of slits, parallel slits separated by equal opaque spaces of equal widths. Now, these lines does not allow through them which are at the gaps between the lines and allow the light and hence forms multi slits. X-rays, what X-rays exactly are? X-rays are high energetic rays fall under the less wavelength region in electromagnetic radiation. Now, as the wavelength of X-rays is small, and the diffraction of X-rays cannot be observed by passing through grating. In 1912, German scientist Lave discovered, scientist's name is Lave, he discovered that X-ray diffraction can be observed by passing X-rays through a crystal. We can see atoms in the crystal does not allow X-rays, while empty space among the atoms allows X-rays. Thus, it is comparable with the wavelength of X-rays, and crystal acts as a source of diffraction, which is known as a source grating. Now, Lave and his co-workers, Friedrich and Krupping, observed the diffraction pattern by passing the X-rays through zinc blende crystal. It is observed that the pattern consists of intense central spot and a series of spots, which is known as the Lave pattern. So what exactly the Bragg's law explain means? Bragg's law explains the condition for the constructive interference of X-rays scattered by a crystal lattice. It is a fundamental equation in X-ray, fundamental and very important equation in X-ray crystallography, especially to determine the structures of various crystals. It is one of the fundamental equation where it shows n lambda is equals to 2d sin theta. As you can see here, we have considered a periodic arrangement of atoms in different planes, that is plane 1, plane 2 and plane 3. Let the interplanar distance among these planes is d. First one is reflects from the top layer beam 2, travels further and enters the second layer, reflects and exists. Thus, the extra distance travelled by beam 2 consists of two segments. Extra path is equals to AB plus BC. Using trigonometry, it is having AB is equals to BC is equals to d sin theta. So, the total path difference lambda is equals to del is equals to 2d sin theta, n lambda is equals to 2d sin theta. So, where L lambda is the wavelength of the X-ray, d is the spacing of the crystal layers, theta is the incident angle, the angle between incident ray and the scattered plane, where n is an integer. So, Bragg's law is the formula n lambda is equals to 2d sin theta, which is a fundamental equation in X-ray crystallography to determine the structure of different crystals. Now, the another method scientists discovered to determine the crystal structure is Lave method. In 1912, a German scientist Lave discovered that the X-ray diffraction can be observed by passing X-rays through a crystal. Crystal acts as a source of diffraction, which is known as space grating. Lave and his co-workers Friedrich and Krupping observed that the diffraction pattern passing by X-rays through zinc blende crystal. It is observed that the pattern consists of intense central spot and a series of spots around it. The pattern is named as Lave pattern. The experimental arrangement consists of source of X-rays, lead diaphragms, and makes the X-rays into a fine beam. You can see these are the beams of X-rays. They are going to pass through the lead diaphragms to make the X-rays into a fine beam. We can see there are the pinholes, and this is the crystalline material, and this is called the photographic plate where the Lave diffraction pattern is focused. Now the X-rays are passed through the pinholes of lead diaphragms to convert them into a fine beam. These rays are allowed into to incident on the crystal, which is held stationary on the crystal holder. The crystal consists of diffraction occurs at the planes which satisfies the Bragg's law. So even in the Lave pattern, in the crystallography, this pattern should obey the Bragg's law, that is n lambda is equals to 2d sin theta. This pattern consists of a series of bright spots corresponding to interference. This pattern corresponds to a set of crystal planes satisfying Bragg's equation n lambda is equals to 2d sin theta. The distribution of diffraction spots depends on their symmetry and its orientation with the incident X-rays. The Lave pattern for a simple cubic structure is shown here. We can see on the Lave pattern of simple cubic structure. That is how there are two methods I have explained so far. One is X-ray diffraction method and second one is Lave method to determine the structure of the crystals. Now the third method I am going to explain is to determine the crystal structure is powder method, or which is also known as Debye-Scherrer method. X-ray diffraction patterns can be studied by taking a sample in either crystal or powder form. XRD provides the structural information of the substance like size, orientation, and interplanar spacing. So Debye and Scherrer, these are the two scientists first observed this method. So that is why it is named as Debye-Scherrer method. It is also known as powder method. It is also known as Debye-Scherrer method. So these are the experimental arrangement. You can see this is the filter, these are the lead diaphragms, entry hole, exit hole. This is the sample powder placed in the capillary tube. This is a cone formed by the diffracted X-rays. This is a cylindrical camera with the film, and these are the transmitted rays. This is the exit hole. So what happens, the sample powder can be prepared by grinding the polycrystalline material such that it contains a nano-sized particle. The speciality of the Debye-Scherrer method rather than X-ray method or Lave method is it is specifically designed to study the structure of even nano-sized crystallites which have random orientations in all possible directions. Thus, the crystallites makes all possible angles with the incident rays. Hence, we can see different orders of reflections are possible. The filter allows only X-rays, and the rays become a finite beam after passing through the lead diaphragms. This fine beam is passed through the entry hole. We can see here this is the entry hole, and the powder consists of number of crystallites in random orientation. This is the crystal. We have placed the sample powder in a capillary tube. We can see which are arranged. They are arranged in a random orientations. And then the diffraction occurs only at Bragg's plane, satisfying here also this powder method also satisfies Bragg's law. N lambda is equals to 2d sin theta. The wavelength of incident X-rays. N is the order of reflection. D is the interplanar space, and theta is the Bragg's angle. Now the X-rays diffracted at atoms at the diffracted rays corresponding to fixed D and theta lie on a surface of a cone with its apex at P. with semi-vertical angle 20. Different cones will be observed at different combinations. So these are the different diffraction pattern observed by the powder method. After this phenomenon, the transmitted X-rays come out from the exit hole. We can see this is the exit hole. This is the exit hole, and the diffracted patterns will be recorded by the camera. As you can see in the experimental arrangement, this is a cylindrical camera with the film. Now, what happens here? The pattern consists of impressions of arcs. So, you can see here these are the arcs formed on either side of the exit hole and entry holes. Exit holes with their centers coinciding with the hole. So, this is the pattern, and we can see here the diffraction angle theta, cos theta is equals to 57.296 S by R, where from the above equation the Bragg's angle theta can be found. From this angle we can determine the interplanar spacing for the first order diffraction by using d is equals to lambda by sin theta. What n lambda is equals to 2d sin theta is the Bragg's law, because we are finding the interplanar spacing here for only for the first order diffraction. When you place n is equals to 1, automatically we will get d is equals to lambda by sin theta. From d value, the lattice constant A of the cubic crystal can be determined. Thus, A and D Miller indices can be obtained. So the merits or advantages of the X-ray powder diffraction method are: monochromatic X-rays can be obtained by using filter. All crystallites will expose it to X-rays and diffraction takes place at all possible Bragg's laws. From the obtained lattice parameters, the crystal structure can be comprehensively studied. Now you can see in the entire unit I have covered all the topics for the unit 2, that is crystal system. We have studied the differences between crystalline and amorphous, and then we have learned some basic fundamental definitions: lattice, basis, unit cell, and then lattice parameters and the properties of the crystal systems, Bravais lattices, and then 7 crystal system properties, and then important definitions like atomic radius, nearest neighboring distance, effective number of atoms, coordination number, and then atomic packing factor. So for atomic packing factor for simple cubic structure, body centered cubic structure, and then face centered cubic structure. And then these are the properties tabulated. And then Miller indices we have studied, interplanar spacing D, and then these are some of the methods to determine the crystal structure. We have studied 3 methods. One is X-ray diffraction, and another one is Lave method, and then last one is nothing but powder method or Debye carrier method, even to determine the structure of the nano-sized crystalline crystallites. So these are the topics which we have covered in the unit 2 crystal systems. Thank you.